Alright, now let's take a look at the Stefan-Boltzmann law, which tells us that the heat, we'll call it capital H, emitted by a black body, which is an ideal radiation emitter, is equal to, or proportional rather, if you will, to the surface area. So the surface area of a black hole would be the surface area of a sphere, times the emissivity of that body, times the Stefan-Boltzmann constant, sigma, this is a constant here, times temperature to the power of 4. Okay, good news here. We have temperature. Area won't be a big problem to find. I mean, we have the radius of the sphere. Emissivity, that's also not too big of a problem because we can just, again, gross oversimplification, but we can assume that and for our purposes, that our black hole is a ideal emitter, giving it this emissivity of exactly 1. So in other words, we just don't include it in our formula. And sigma is a constant. So basically from here, we are going to be able to rearrange for our heat. So we had come up with an equation for the heat, in other words, the rate at which the black hole is losing energy, right? That's the power emitted by the black hole. Now, in order to find the lifetime of our black hole, T sub lifetime, this will be the total energy of the black hole, not to be confused with the Hawking radiation of a single Hawking quanta being emitted from the black hole, but the energy of the entirety of the black hole, divided by the rate at which it's losing power. Okay, now I want to bring your attention to one thing. Before I solve this, I just want to just quickly note that in order to solve this correctly, we have to treat this as a differential equation because, of course, our power is changing as our mass, as more and more mass evaporates. But we're going to neglect that and take our power at the point with our initial mass, alright? So we're going to assume we have a linear equation here so that we don't have to solve a differential equation. Now again, as I said, right, keyword timescale, we're not looking for a rigorous answer, we're looking for within a couple orders of magnitude, really. Okay, so let's begin solving this one. So T lifetime is approximately equal to the energy of the whole black hole. Now in Einstein's famous formula, of course, mc squared, in this case m being mass of the black hole, that tells us what the mass of the whole black hole is. So, mass of the black hole, c squared, times, we'll say, just to separate them a little bit, times 1 over heat, which is this whole thing, which is A emissivity sigma T to the 4. Okay, so all I've done here is I've just reduced the clutter of the board. I haven't changed anything about our equation. I've just expanded terms. I'll remind you that this is our energy term. This is 1 over our area. Now this is the surface area of our black hole, which I've gotten rid of. Remember, the surface area would be 4 pi r squared. I've just included r squared. Remember, this is r, so this would be 1 over r, right? Now keep in mind, all I've done here is I've gotten rid of the 4 pi, which again, it's negligible for our purposes. Not really, but still. This is 1 over our Boltzmann constant. It's a constant here, nothing's changed there. And this is 1 over our temperature. So I've simplified here, and I have this equation remaining for our T lifetime. Okay, so let's do something with it. Let's find the time it would take within a couple orders of magnitude, because remember we have gotten rid of many sub 1 order factors, many pi's, many 2's, whatever, right? Still though, we'll get an answer within a few orders of magnitude. And let's solve this equation, because our only variable here, it's worth noting that our only variable is the mass of the black hole. Everything else is a constant. So this is our formula right here. Now keep in mind, I could have solved this with a differential equation and gotten a more rigorous answer, but still, remember, no calculus. Okay, so let's solve our equation, or let's solve for t lifetime when, if the mass of our black hole was exactly one solar mass, exactly the mass of our sun. So if our sun turned into a black hole, how long would it take to evaporate? So if you plug in all the numbers right, turns out your answer in years is 1.4 times 10 to the power of, wait for it, 63 years. Now that's an astounding number because for reference, the universe has existed for an order of magnitude of 10 to the power of 10. Okay, so 10 to the power of 63 is absurd. I mean, we have existed for over 10 billion years, this universe has, and a black hole the mass of the sun, not the size, the mass of the sun will exist for 53 orders of magnitude longer. Now I'll remind you, this is logarithmic. This is not multiplicative, this is logarithmic. This is exponential here. Okay, now keep in mind there are black holes much larger than the sun. We have black holes who contain the mass of billions of solar masses. So imagine, for example, a billion cubed. That's how much bigger this value is going to be. That is why black holes will be the last surviving objects in this universe at the heat death.